AI is not slowing down, but the hardware running it might be about to hit a wall. Not a compute wall, but an interconnect wall. And the fix isn't having a better transistor. The fix is light. Hi, I'm Devansh, and this is Voltage Drop. So let's start with the actual problem. When you're training a frontier AI model, something like ChatGPT 4, Gemini, Claude, whatever, you're not running it on one chip. You're running it across thousands of GPUs, all constantly talking to each other, passing data back and forth. The compute side of that, we're actually good at this. The problem is the communication. Every time data moves between two chips, it travels across copper. And copper has limits. It generates heat, it eats power, and the faster you push it, the worse these problems get. The industry's been working around this for years, but at the scale AI now operates at, we're talking petabytes of data moving between GPUs constantly, copper is becoming the actual bottleneck. Jensen Huang has basically said it out loud. He says optical links between GPUs are not reliable enough for production yet. Now, he said it as a caveat, but the fact that he's even saying the words optical links tells you exactly where this is going. So, what are optical links? What's this actual alternative here? It's light. Photonic chips use photons, particles of light, instead of electrons to move and process information. Now, here's why this is a big deal. Photons travel at the speed of light, obviously, but the more practical thing is they don't generate heat the way electrons do. They don't interfere with each other on a crowded wire. You could actually send multiple signals down the same fiber at the same time as long as these signals are at different wavelengths. They don't collide and they just coexist. So this is called wavelength division multiplexing, and it's the reason a single fiber optic cable can carry more data than you'd ever get out of copper. So the idea of putting that on a chip has been around for decades. The challenge has always been manufacturing. How do you actually build this at scale? And the honest answer is the pressure from AI is the thing that's finally forcing this problem to get solved. So there are three main material platforms people are building on right now. So first is silicon photonics. Silicon is great because it's what the entire semiconductor industry already knows how to use. TSMC knows silicon. Global Foundries knows silicon. You could run photonic devices through existing fabs with existing equipment. Now, the catch is silicon doesn't emit light. You can guide light through it, you can modulate it, you can detect it, but to generate photons in the first place, you need something else. And that something else is indium phosphate. It's a compound semiconductor that's excellent at generating and amplifying light. The problem is that it's very expensive. It's hard to work with at scale, and there are only a handful of suppliers in the world. NVIDIA has already been locking up indium phosphate laser capacity so aggressively that lead times on those components are stretching past 2027. So just let that sink in. They are buying supply 2 years in advance. That's how serious this transition is getting. Now, the third platform is thin film lithium niobate, also known as TFLN. Now, this one is newer, extremely good at modulating light with very low power. We see startups gravitating towards it specifically because it solves some of silicon's limitations. And the direction the whole field is going is hybrid. It's combining all three on the same package. Silicon for the manufacturing backbone, indium phosphate for the light generation, and TFLN for the modulation. None of them alone is the answer. However, together, they may be. Okay, so where is this actually deployed today? What's the status quo? So the biggest immediate application is data center interconnects. Not the chips doing compute, but the links between these chips. A startup called Light Matter out of Boston makes a photonic chiplet called Passage. It sits between GPUs and handles communication using light instead of copper. Now, their numbers are their 3D co-packaged optics gives you 2.7 times reduction in time to train on frontier AI models. Now, this is a real claim on real workloads. Another company called Ayar Labs makes something called Teraphy, Teraphy, another optical chiplet. Microsoft and Google led a 155 million round into them. They've shipped over 10,000 optical chiplets already. Then there's Quant out of Germany, which is going further. They're building an actual photonic processor, not just an interconnect. Their NPU2 is built on thin film lithium niobate and is targeting shipments in the first half of this year. On the big company side, NVIDIA's next-gen AI networking switches are being built around co-packaged optics. Global Foundries acquired Singapore's Advanced Microfoundry in late 2025, specifically to scale silicon photonics capacity. Tower Semiconductor is putting $650 million in to triple their silicon photonics output by mid-2026. This is not a research project anymore. We see this supply chain forming in real time. But here's where it gets more interesting, and where the engineering is genuinely hard. The dream version of this isn't just using light to move data between chips. It's using light to actually compute, to do matrix multiplications, to do convolutions, the core operations in neural networks. There are limits to implement those optically, and in principle, they'd be fast and efficient in a way electronics just can't match. But doing this reliably at a manufacturing scale with real products, that's still unsolved. The timeline most researchers agree on is data center interconnects are happening now. Photonic compute at scale is probably a 2030 story. And there are real blockers. Light is really hard to store. There is no optical equivalent of a memory cell, which means any real system has to be hybrid right now. Photonics for movement and some compute, electronics for logic and memory. So this integration is very complex. There's also Jensen Huang's reliability point. Optical systems are sensitive to temperature, vibration, manufacturing variation in ways copper just isn't. Getting that to the 5 nines uptime standard that hyperscale data centers require is an ongoing engineering problem. And it's definitely not solved. So, what's the actual trajectory here? Here's my prediction. In the next year or two, co-packaged optics becomes standard in AI switches and high-performance networking. The 1.6 terabyte transceiver becomes the new baseline. Silicon photonics manufacturing scales up significantly. And in the next 5 years, optical chiplets start appearing closer to the compute itself, inside the package, not just between packages. And in the 2030s, maybe, if the engineering gets solved, photonic processors start handling actual compute workloads. The full vision of a chip where light does the work, not just the communication. That's still out there. But the gap between that vision and reality is closing faster now than at any point in this field's history. So, because the pressure is real, AI training clusters are approaching the power draw of small cities. The economics of copper at scale just don't work, and light is the only thing that makes physical sense as a replacement. So the thing I keep coming back to is this. For most of computing history, the transistor was the unit of progress. Having smaller transistors meant having faster chips. And this just keeps repeating, and it's the end of the story. What photonic chips represent is something different. It's not just a better version of the same paradigm. It's a fundamentally different substrate for computation. So last episode we looked at neurons, right? Biology replacing silicon for certain problems. This episode, it's photonics replacing electrons. And both of them are basically asking the same question. What are the actual limits of silicon, and what comes after? I don't think the answer is just one thing. I think computing stops being monolithic. Different substrates for different jobs, right? Light for communication and eventually some compute, neurons for certain learning problems, and silicon for everything we see that it's already great at. That fragmentation is probably the most interesting story in hardware right now, and we're going to keep following it. Links to Light Matter, AR Labs, and the Quant NPU2 are in the description. Please consider subscribing and liking. I'm Devansh, and this is Voltage Drop.